So you guys have been working on velocity time graphs, position time graphs, and acceleration time graphs, and I just want to go through and make sure that you guys are on the right track and doing things all right. So we're going to go through and look at a couple of graphs, and I'm going to explain a few things. Okay? And you guys know from before that if I have a velocity time graph that slopes up, and then let's say it stays horizontal for a while, and then we'll have it come back down this direction. Okay. There's a lot of information right here in this graph, right? This velocity time graph tells me about an object's speed and position at every instant in time. So it gives me instantaneous speed and instantaneous direction. So if we look at this first time interval from 0 to 2 seconds, okay, we can say that it speeds up and moves away, and we can say that because the velocity is positive and becomes more positive. So I'm going to say speed up away. But I can say more than that, right? We learned that last time. If I take a look at the area underneath this thing, if I look at the area during this time interval, I can also find the change in position of the object, right? So I also know that delta x, change in position, is equal to area, and since that's a triangle, the area of that is 1/2 base times height, which is just 1/2 2 times 2, which is 2 meters. Now why is it meters? Well, we're taking a velocity as our height, okay, which is 2 meters per second, times a time, 2 seconds as a base, times 1/2, and so that's where the 2 meters comes from. Okay, so I know more than just that it's speeding up and moving away. I also know that it's gone 2 meters. We can do a similar process in the next time interval. This time interval, from 2 seconds to 4 seconds, we can say the object's moving away at a constant speed of 2 meters per second, and it does that for 2 seconds. Okay, and this one we don't think of it as an area, but it is. Okay, we take rate times time to get distance. Well, you're taking a distance or a rate of 2 meters per second times a time of 2 seconds, right? That's our time interval, and that's 4. So 2 meters per second for 2 seconds gets you 4 meters. For our next time interval, okay, we check this one. We have the same thing we had going on over on the other time interval, except that this time it's not getting faster, it's getting slower, right? Because this is starting up here at 2 meters per second and ends down here at 0 meters per second. So for this time interval, it's still moving away because it's still positive, it's just getting slower. And so we've got, again, an area of 2, 1/2 base times height. So this area was 2 meters, this area was 4 meters, and the first area was also 2 meters. Okay? Now, and there's one more time interval here, right? So let's go to that last time interval. What happened when it crosses the axis? Well, that's when it switches direction. So if I look at just this area, okay, it's got a -2. Okay, why is it negative? Well, if we look at our height, right, for the triangle, it's this -2 meters per second. So it's a negative area. Okay. Now that's a lot of information, and from that I can tell you that the overall change in position of this object, the total delta x for the whole thing, is going to be the first 2 meters it went, then it went 4 more meters, and then it went 2 more meters, but then it came back, so minus 2 meters, and so the total displacement is 6 meters. Okay, and I got that just from the areas on here. Now, can I do anything with that? Well, I can't make a position time graph just from that information because I don't know where it started, but I can make a position time graph if I know a starting point. Okay, so let's say my initial position, my xi, was 1 meter. Okay, so right here at 1 meter, I started, and this object, it got faster and moved away, and we know it moved 2 meters away. So, and it did it in 2 seconds. So in 2 seconds, I've got to get 2 meters away, which is going to put me up here at 3 meters, right? That's 2 meters past 1. But while it's doing that, it's got to get faster. Okay? And so while it's speeding up, it starts flat but curves up. Okay? So maybe I'll do this in green just so it matches my time interval over there. Okay, so let me grab the green marker. Alright, so it starts at 1 meter, it's got to get to 3 meters, and while it's doing that, it's speeding up, which means this line is curved. Okay, now for our next time interval, we know it goes 4 meters, but we're not so interested in that. Maybe we are, but so it's got to go 4 meters, so that's from 4 more meters is all the way up to 7, and it does that in 2 seconds. But to me, this one is easier to think of in terms of slope. Remember, velocity is graphing the slope of position, and so the slope is 2, so rise over run, 2 over 1, 2 over 1 for 2 seconds, and we got there. Okay? And apparently I didn't plan this one out very well because I'm going to be out of position, but that's okay. I just need one more row up here, okay? Because I need to go 2 more meters in 2 more seconds. Of course, I got to be careful, right? So 2 seconds is going to put me up over here, but I got to get 2 meters further away because I covered an area of 2, so I'll be up here. Okay, but what's going on during this time interval? Well, the object started fast. 2 seconds, I'll be over here, and got slower. Okay, so this has got a curve opposite of what that green one did. So it's got to go like this: start steep, get less steep. And then the last time interval, it's switched directions, so now it's got to move closer. It's got to move 2 meters closer. It's got to do that in 2 seconds. So it's going to be down here, 2 meters closer, and it's going to start slow, which is flat, and get steeper as it goes, so it curves. Now I said down here that the total displacement was 6 meters. Okay, so let's check it. It went from 1, it ended up at 7. That's a total displacement of 6 meters. So we're good to go there. Okay, so from a velocity graph to a position graph is easy if you know the initial position, right? Because the area under a velocity time graph gives you change in position. The other way around is also fairly easy. We can do the same process in reverse. We look at the slopes. We say, all right, this slope started small and got steeper, so this velocity started at 0 and went higher because it's moving away. It covered 2 meters, so the area needs to be 2. Okay, the slope right here is 2, so my velocity right here is 2. The slope right here started at 2 and went to 0, so my velocity started at 2 and went to 0. The slope right here is 0 and went to -2, so my velocity was at 0 and went to -2. Okay, so we had these relationships between position and time graphs that we already know, and what this lab did was it allowed us to extend it one step further. It's like, okay, so to go from position to velocity, I'm going to graph slopes, because the rate of change of position is velocity. Well, the rate of change of velocity is acceleration. That's why acceleration has units of meters per second per second. Okay, if you do the math on that, that's a meter per second squared. It tells you how fast the object, how much faster the object gets every second. Okay, I know that this object started at rest because it started with an initial velocity. I know it got faster for the first 2 seconds. That means its velocity changed, and that's reflected by this line. Okay, how much was it changing? Well, after 1 second, it was going 1 meter per second. After 2 seconds, it was going 2 meters per second. That's a slope of 1. The slope of this line is telling me its acceleration. So if I grab that green marker over here on the acceleration time graph, I know that the acceleration is 1 meter per second per second. I'm just graphing the slope again. I'm going one step further. Okay? For the next 2 seconds, it's still moving, but it's no longer accelerating. It's moving at a constant speed. It's moving at this 2 meters per second. So my acceleration graph goes all the way down to 0 and stays there. Okay? Acceleration doesn't indicate position. It doesn't indicate speed. All an acceleration time graph is to tell you if the speed is changing or not, and if it is changing, at what rate it's changing. Okay? So our first time interval, yes, it's a non-zero acceleration, so the speed is changing, and it's got an acceleration of positive 1 meter per second per second. This next time interval, 4 to 6 seconds, what's happening to that object? Well, during that time interval, the object is slowing down, and it's getting slower at a rate of -1 meter per second every second. Okay? So just like before, I'm going to graph my slope, and it's going to come down here to -1. What about this time interval? well, it's still a slope of -1, so my acceleration is a -1. Okay? Now, wait a minute. What does that mean? Does that mean these two motions are the same? No. What it means is acceleration does not indicate direction. Okay? A positive acceleration does not necessarily mean the object is moving forward, and a negative acceleration does not mean the object is moving backwards. A positive acceleration does not mean an object is speeding up. A negative acceleration does not mean an object is slowing down. You have to look at the two together, and we're going to see that tomorrow or maybe today in lab. Okay, so just like before, an acceleration graph is generated by graphing the slope of a velocity time graph. And just like before, if I look at the area under an acceleration time graph, I'm going to get the change in velocity for that time interval. Let me demonstrate. Okay, so if we take this first time interval from 0 to 2 seconds, if I find the area of this section, that area, that's just a rectangle. Okay, the area here is 1 meter per second times 2 seconds, and that's 2 meters per second. That tells me that over these 2 seconds, the object got 2 meters per second faster. If we look at our velocity time graph, it went from 0 to 2. It did get 2 meters per second faster. The area here, the area in the middle there is no area because it's got no height. That's 0. That tells me that the velocity didn't change. Well, at the beginning of this interval, it was 2. At the end of this interval, it's still 2. It didn't change. What about this last interval? This last interval over here is 4 units long. 1, 2, 3, 4 units long, and -1 meter per second squared high. So that means this has got an area of -4 meters per second. That means this object needed to change its velocity by -4 meters per second. Did it? Well, sure. If we look right here at the beginning of this time interval, it's moving at 2 meters per second. At the end of this time interval, it's moving at -2 meters per second. -2 minus a 2 is -4. It got 4 meters per second changed, and it did it in a negative direction. Okay, so the acceleration time graph is just one step further than a velocity time graph. Okay, so it's just like going from position to velocity is velocity to acceleration. Velocity to position is acceleration to velocity. Same process, just one step further.